So moving along. So as we start to build up our wave function, a good place to start is for molecular hydrogen. It's our simplest thing that we could describe as a molecule. Next to H2 plus, of course. H2 plus would be only a 1-electron system. But for now, in this H2, we've got a 2-electron system designated by R1 and R2. So that would be electron number 1, and that would be electron number 2, the position of each. Chi H1SA and chi H1SB are atomic wave functions of each respective hydrogen. So I'll say atomic wave functions. And so chi is used, but it's all the same as any other letter. It doesn't matter. It's just a letter. And so what we gather from this is our psi H2. I'm going to erase this circle because that's bothering me. Our psi H2 is a separation of variables of the total wave function, right? So I've got, I'll say atomic wave function for B, and then we know that this is the atomic wave function for atom A, and of course our H2 molecule, you know, is HA bonded to HB. Okay, so simplifying our notation, instead of saying chi H1SA R1, I'm just going to say A1. All right, so all of this, right, our atomic wave function will just represent simply as A1, and all of this, our atomic wave function for atom B can be represented there. And now, of course, we have to remember our special case of the Pauling exclusion principle, and that is we have to be able to exchange labels on the wave function. And if I do that, it has to change sign. And so what ends up happening now, we get this possibility, right, that we call a basis set. These are the two terms in our basis set, which could be A1B2 or A2B1. And when we put that basis set together to make a superposition of those atomic orbitals, we get A1B2 and plus or minus A2B1 because we don't know which one is the acceptable changing of labels. And so in the superposition, both the plus and minus state are possible. And there are consequences between those plus and minus states. And we'll deal with those as we go. So for now, if we talk about what these things all look like, so I'll remind you what this curve is right here. So for example, that exponentially decaying curve, that would be psi H1S, which we know is basically some normalization constant and e to the negative r divided by a, right? It's our hydrogen 1s wave function, which is that decaying exponential. And so now you can see in the background that red area, that's representing the spherical wave function for psi 1s. And so the decay we're seeing right here is how the wave function decays for positive radiuses going out this way. I'm going to erase that so that it's not confusing. And then, of course, on this side right here, this also shows you the wave function decaying out to negative radiuses because, right, we have a sphere. So it can be noted with sphere radius going this direction or sphere radius going this direction, right? And so we see the same thing with atom B, okay, right, this blue area. So this blue area represents atom B, okay? And so also we can draw the same conclusions, right, where we know that this is the radius of atom B, and of course this is the radius also of atom B, just out to negative or positive radii, right? And it's going to decay in the same fashion. And of course, when we switch the labels of these, they're spherically symmetrical, so nothing happens, or at least nothing dire happens. And so now if we look at just the plus state, I'm going to box this up. If we look at just the plus state of our superposition, okay, we get what's called enhanced electron density owing to constructive interference, right? I'll just say constructive interference, okay? And that constructive interference, right? Notice like when we add the two curves together, right? There's now, this is the wave function, right? So there is a positive non-zero value. That tells us there is finite probability of finding the electron between these two regions. And so what are these two regions? Well, each of those regions represents a nuclei, right? So there's a proton there, and there's a proton there. And we see when we get those two wave functions close together and their two atomic wave functions interfere constructively, we get positive and finite probability of finding the electron between those two protons, okay? Great, so moving on, okay? So we also have to now add in this proper spin wave function to describe the singlet state that's created between them. And I'm not going to get us into a whole lot of detail on these spin wave functions. I kind of mentioned that before. We just accept that, we would tack that on to the result because we would have, combinations of atomic wave functions, but then we also have to consider the spin correlation between the two electrons. And we're not going to go into that level of detail.